Welcome to the 15th class of this course, and let me summarize whatever we did in past few classes in this Legendre polynomials. So first we introduced the Legendre differential equation, then we solved it and we got a series solution. Okay, this is a general solution we got, and which is a linear combination of two independent linearly independent solutions. So these y even and y odd are two such series solutions. And then we got the Legendre polynomials. Okay, this PLX, where L can take values from 0 to infinity. Okay, 0, 1, 2, 3, all the integers. And then we used Rodriguez formula and the method of generating function to generate the Legendre polynomials. Okay, and then we showed that these Legendre polynomials, this PLX, those are orthogonal to each other. Okay, so it's P0x, P1x, P2x, P3x, those are orthogonal to each other. And in that context we introduced what do we mean by orthogonal, what do we mean by dot product between two functions. Okay, so I am assuming that we guys all know what does it mean by dot product between two vectors. Okay, and the dot product between two functions are defined as, let's say there are two functions like fx and gx, then the dot product between them will be defined as fx gx dx from a to b equals to, or this is the dot product. Okay, this is the dot product. So similarly, the dot product between two different Legendre polynomials is basically -1 to 1 PLX PMX dx. Okay, so the Legendre polynomials, those are defined in the interval of -1 to 1. Right? So and orthogonality means the dot product is 0. Right? So that's what here it is showed that integration -1 to 1 PLX PMX dx equals to 0 if m not is equals to n. Okay, so if you take two different Legendre polynomials, then they are orthogonal to each other. But don't try to think in terms of directionality. Don't try to think that okay, PL is a vector in some direction and PM is some vector in some other direction which has 90-degree angle. There is no meaning of that. These are functions. These are not directional vectors. Okay, so those things I have described in the last class. So today I will talk about normalization. Okay? Normalization means, so let's say if we are given a n-dimensional Cartesian vector, let's say v equals to, then I can write it as let's say v1 e1 hat plus v2 e2 hat plus dot 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 plus vn en hat. Okay, this e1 hat e2 hat dot 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 en hat, these are all the perpendicular or orthogonal basis vectors. Okay, and as we're talking about an n-dimensional vector, then there will be n such basis vectors basically, and it can also be written in terms of this tuples, like this v1 v2 dot 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 vn. There will be n tuples because we have an n-dimensional vector. So the magnitude or mode of v is basically, it is analogous to the length in case of three-dimensional vectors, directional vectors. That is v dot v. Okay, and which is nothing but dot product of the vector with itself, that is v1 times v1, that is v1 square plus v2 square plus dot 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 vn square. Okay, and normalization means if we want to normalize this vector v, that means we want to find, so the definition is basically the vector v divided by norm of v. Okay, this is mod of v or norm of v. And in case of three-dimensional directional vectors, it means like finding a unit vector in the same direction as v. Okay, but in case of n dimension, there is no such notion as a direction. So it's just the algebra that we are following. Okay, so then it is basically v1 divided by norm of v comma v2 divided by norm of v, and so on, vn divided by norm of v. So this is how we do normalization of n dimensional Cartesian vector. Okay. So now here we are talking about normalization of functions. So we are talking about normalization of this PLX, Legendre polynomials, right? So here the dot product is defined as, so let me state it again, the dot product between two functions is defined as okay, this is how the dot product is defined. Okay, this is how this f dot g is defined, right? So in that case, if we want to have a similar kind of quantity analogous to this norm of a vector, then it is basically, let me call it, let me use a notation like norm of PLX, okay, which is nothing but the dot product of PLX with itself. Okay, that means from -1 to 1 PLX star PLX dx. Okay, and this star is basically complex conjugate. So if we are dealing with complex numbers, in that case this star will be important, but here this PLX, these are all real quantities, right? So in that case, whether you are taking a complex conjugate or not, it will not make any difference. Okay, so I can just remove it. So this is basically norm square. Okay, this is basically norm square, norm of PLX and square of that. So it is analogous to length square in case of three-dimensional vectors, but here there is no notion as length. Okay, direction and length. So it's just the algebra. Fine. So now the question is, if let's say a vector, for example, if there is a Cartesian vector, if it is normalized, in that case, so for example, if this v is normalized, which means that v dot v equals to 1, right? Dot. So for a normalized vector, the dot product with itself will be 1. That's the meaning of normalization. Okay, here now if someone is asked like whether this PLX, these Legendre polynomials, are they normalized? The answer is no. Okay, and to check that whether those are normalized or not, you need to calculate this quantity, the dot product of PLX with itself, and I will show that okay, it doesn't equals to 1. Okay, so these are not normalized yet. So let's find out what's the value of it then. If it's not equals to 1, then what is it? Then what is it? Okay, so the question we're trying to answer is, are PLXs normalized? That is is it 1, or not? Okay, so that's what we want to know. Okay, so to find out the value of this plx dx, integration of plx dx, let me start with a recurrence relation that I showed in 12th class. Okay, so I will start with this recurrence relation B. I will start with this recurrence relation B. So it is, if I write the right hand side first, then it is LPLX. Okay, it is LPLX. So it is LPLX equals to X PLX dash X PLX dash minus PL minus 1x dash. Okay, so this is already proved in class 12. Now what I will do is I will multiply both side with PLX. Okay, so then it will be L PLX square equals to X PLX times P dash LX minus PLX P dash L minus 1x. Okay, and now what I will do, I will integrate both side. So L, I can put it outside because it's a constant, minus 1 to 1 PLX square dx equals to integration from minus 1 to 1 X PLX P dash LX dx minus integration from minus 1 to 1 PLX P dash L minus 1x dx. Okay, and now this last term, so that, so the last term is 0. Okay, so this is given as homework for the last class. Okay, so this term is 0. You can just just understand it from the fact that this P dash L minus 1x, so P L minus 1x, it's a polynomial of degree L minus 1. Okay, so P L minus 1x, it's a polynomial, and the highest power of x here for P L minus 1x present is L minus 1, right? And if I do P dash L minus x, then the highest power of x present is L minus 2. Okay, so that means if I want to write it in terms of Legendre polynomials, so then what I will write, it will be sum over of n equals to 0 to infinity, 0 to L minus 2, let's say Cn Pnx, right? So it will go up to L minus 2, and then so there will be terms like P0x, P1x, P2x up to L minus 2, up to P of L minus 2x, right? And then it is being dot product with PLX. So that case, all the terms will be 0 just because of the orthogonality property. Okay, so this is given as a homework in the last class. I will not prove it again, but the argument is, I think it's well understandable. Okay, now I will concentrate on this second term, on this term. So if I treat it as first function, and if I treat the whole thing as a second function, and if I okay, let me write it in a different way. Minus 1 x times, I can write it as 1 by 2 ddx of plx square, and there is dx. Okay, so I am writing only this term, okay, only this term. Okay, so then it equals to, so if you do the derivative ddx of plx square, then there will be a 2, so this 2 will cancel, and there will be plx and there will be p dash lx. Now if I do integration by parts, then if I treat it as the first function and this is the second one, then it will be like it will be x by 2, okay, integration of x by 2, sorry, integration from minus, sorry, integration of ddx of plx whole square dx, right? And the limit is from minus 1 to 1 minus integration from minus 1 to 1 ddx of x, which is eventually 1, okay, and times half times integration of ddx of plx whole square dx, okay, times dx, right? This is the integration by parts or partial integration. Okay, so now if I do this integration, then it is x by 2, and this integration is basically plx whole square. Okay, so it is basically plx whole square, and the limit is from minus 1 to 1, right? And the second term, then it is minus 1 to 1, so ddx of x is 1, let's not write it, so the half is there, and if I do this integration, then it is just plx whole square. So we have plx whole square dx, okay, and so which is basically okay, so if I put the limit, then it is okay, so plx pl1 is, this is also I showed that like pl1 is 1 and pl minus 1 is minus 1 whole to the power l, okay, and we are doing square of that, so that means pl1 square will be 1 and pl minus 1 square will be minus 1 to the power 2l, okay, that means it is minus 1 square whole to the power l, which is nothing but 1, okay. So then if I put the limits, then it is, if I put the upper limit, then it is 1 by 2 minus, if I put the lower limit, then it is minus 1 by 2, and then if I take this minus outside, then it will be then plus half minus 1 by 2 minus 1 to 1 plx square dx, okay. This is the this is as this term is 0, so this term will be basically the total right hand side. Okay, so let me write down then the whole equation. Then the left hand side is L into minus 1 to 1 PLX whole square dx equals to this half plus half. Half plus half is 1 minus half times minus 1 to 1 PLX square dx. Now we are almost done. So now if I take this term left hand side, then what we will get? We will get L plus half. Okay, I can take that. So I can take this integration common, and then that we are left with L plus half. It is PLX whole square, because in both of the terms there is this term is common. Okay. So equals to 1, which implies minus 1 to 1 PLX whole square dx equals to, so this term, this L plus half, it can be written as 2L plus 1 by 2. Okay, and if I take it to the right hand side, then it will be 2 by 2L plus 1. Okay, so this is the inner product or dot product between dot product of two PLs. Okay, and it's not equals to 1. So it is not equals to 1. That means our Legendre polynomials, those are not orthonormal. Okay, so if you want, so it basically says that as it doesn't equal to 1, that means PLXs are not, it's a dot product of PLX with itself, and it is not equals to 1. So that means these are not normalized. Okay, normalized, but those are orthogonal. Okay, to normalize them, we need to divide it with its norm, and which is basically root under of that. So with root under of q by ql plus 1. Okay, this is the norm square. It's a dot product of PL with itself. So basically normalized, or I can write it as orthonormal set of Legendre polynomials. Those can be written as, if I divide it with this quantity, then it is basically root under 2L plus 1 divided by 2 times Px. So this for different L equals to 0, 1, 2. So these are the orthonormal set of Legendre polynomials. Orthonormal means orthogonal. So it means orthogonal, that we already proved in the last class, plus normalized. Okay, so this is how we can normalize the Legendre polynomials. So remember that this PLX, those are not normalized. Okay, and so with the help of this relation, let me call it, so if I call it equation 1, if I call this orthogonality property as equation 1, and if I call this property as equation 2, okay, then I can combine them combine equation 1 and 2, and I can write as integration minus 1 to 1 PLX times PMX dx equals to 2 by 12 plus 1 delta of ml. Okay, so it basically says, it's a very important relation which basically says, so this delta ml means, let me define this delta ml. Delta ml means it's 0 if m not is equals to L, and it's 1 if m equals to L. Okay, so it specifies both the orthogonality property and the normalization factor. Okay, so it basically says, okay, if L not is equals to m, in that case those will be orthogonal and we will get 0 in the right hand side, and if L equals to m, then it is basically a dot product with itself and we will get some factor which will be needed for normalization. Okay. So basically what we have proved is, in this class and in the last class, if I combine them, so then what we have proved is basically this. So just like in case of Fourier series, we had like a basis set of normalized orthogonal set of basis like 1 sine x cos x, okay, comma sine 2x comma cos 2x, okay, comma dot dot dot, infinite number of such basis vectors, and for a function which satisfies the Dirichlet condition, I can write it as a linear combination of these vectors. Okay, if I call it like E0, E1, these basis vectors are, if I denote as E2, E3, E4, so then it will be linear combination of let's say alpha I EI, I equals to 0 to infinity, and that's basically the Fourier series, right? And this is just like, vectors, like if these are the basis vectors, then any vector can be written as a linear combination of these basis vectors. Okay, and the same idea I will use for these Legendre polynomials. Okay, so these Legendre polynomials, those are orthogonal to each other. So that means this P0x, P1x, P2x dot dot dot, PLX dot dot dot, infinite number of this Legendre polynomials, it forms a set of orthogonal basis vectors or orthogonal vectors which can be treated as basis. Okay, and in that case, any function, so in that case the claim is basically any function it is underlined that it should be a well-behaved function. Okay, well-behaved means it is not diverging in the defined interval and all. Okay, so any function on x belongs to -1 to 1 can be written, any function, let's say fx, can be expressed as a linear combination of PLXs. Okay, so just like Cartesian vectors, so if we have three basis vectors I, j, k, then any vector in 3 dimension I can write it as a linear combination of I, j, k. Okay, so same idea, same algebra will be followed here, but there is no notion of directionality, so it's kind of an abstract thing. Okay, so yeah, so we shall says that fx, okay, fx equals to sum over of, for example, cn or cl plx l equals to 0 to infinity. So these can be done. Okay, so let me use an example of how a function can be written in terms of these Legendre polynomials. Okay, this is called a Legendre series, basically. Legendre, just like Fourier series, these are called the Legendre series. So we are writing a function in terms of as a linear combination of Legendre polynomials. So let me give an example. Okay, so example is basically you are given the given function fx is basically 0 in the interval of -1 to 0 and 1 from 0 to 1. Okay, so the function looks like this. So this is -1, let's say this is 1. Okay, this is the x-axis and this is the fx. Okay, the function looks like this. Okay, so we are asked to, what we are asked to do, so we are asked to write this fx as linear combination of cn, sorry, I can write cn also, no problem, cl plx, l equals to 0 to infinity. Okay, so we already know this plx's, so what we need to find then, these coefficients. Okay, so our job is now to find these coefficients and then we are done. So let me do something which is applicable in general and then I will put this function. Okay, so let me, for now, let me treat f as a general function, not this particular function. So fx is basically sum over l equals to 0 to infinity cl, these are constants, and then plx. Now what I will do is, we write fx here. What I will do is, I will multiply both sides with pmx, okay, with pmx, and then integrate from -1 to 1 with respect to dx. Okay, why I am doing that? Where is the idea is coming from? It is the same idea. So pay concentration here. So for example, in case of vectors, if you think, so let's say if you have a vector v which is in 3 dimension, for example, where the x component or I component is Vx, y component is Vy, and z component is Vz. Now if one wants to know, okay, how do you get the x component, then what you will do? So here this I hat, j hat, k hat, these are the basis vectors. Okay, so these are like this PLXs. So what you will do, if one wants to know the component along this I hat, you will dot product with I hat, both side. In that case, you will Vx I hat dot I hat plus Vy j hat dot I hat plus Vz k hat dot I hat. And because of this I hat, j hat, k hat, those are orthogonal. So these terms will be 0. Dot product with, so j dot I and k dot I will be 0. And we can then find that I dot I will be 1. And then we can find this Vx. Right? The same idea is applied here. So here, instead of this I hat, j hat, k hat, what we have is this PLXs. And the L can take any values like 0 to 1, 2, 3, 4 into infinity. And this V, this general vector, is basically this general function. Okay. And we are asked to find out CL. CL means this Vx, these coefficients, component along those basis vectors. Okay. Here Vx is a component along I hat. Here this CL, you can consider it as a component along PL. Okay, PL is a basis vector similar to I hat. So what then we will do? So just like we did, we did a dot product with this I hat, with this basis vector, and use the property of orthogonality to cancel all the other component effects. We are doing here the same thing. So here we are. So if we want to know what is Cm, the mth component, let's say L is a summation index. So let's say what is the Cm, the mth coefficient. In that case, we will dot product. We will do dot product with Pmx. Okay. So that's what we are doing. So all these tricks, all these ideas, these are coming from this, this 3-dimensional, this Cartesian vectors. Okay. But here we will only be dealing with abstract algebra. We are not talking about any directionality. Now, if I do this dot product, then we already know what's the value of this dot product. It is 2 by 2l plus 1 times delta of lm. Okay. So that's we already showed here. This, right? So it's basically, it implies -1 to 1 fx pmx dx equals to sum over L equals to 0 to infinity CL 2 by 2L plus 1 times delta of Lm. And what is delta of Lm? Delta of Lm is a chronicle delta function. It means its value is 1 only when L equals to m. That means in the summation terms, only when L equals to m, only that term will survive. Otherwise, if L not equals to m, all those terms will be 0 because of this delta factor. Right? The only term surviving is basically when L equals to m. That means Cm. Okay? 2 m plus 1. And from there I can write Cm equals to 2m plus 1 divided by 2 from -1 to 1 fx pmx dx. So if I want to find mth coefficient, then this is the formula. Or so this is m, it's just an index. Okay, so I can, instead of m, I can write as L. If I want to find CL, then it is basically 2m plus 2L, sorry. So I'm replacing m by L, this 2L plus 1 by 2 -1 to 1 fx plx dx. So this is a general formula okay, where this fx is basically sum over CL PLX, L equals to 0 to infinity. This is a general formula to find these CLs, okay, these coefficients, right? So, and here also we want to find these coefficients, okay, and now instead of this general form of a function, we have a specific function, okay, that is given by this. So using that definition of this, that if specific function, we will calculate what are the values of the CLs, okay. CL is basically 2L plus 1 by 2 minus 1 to 1 fx PLX dx. And what is fx? So fx is by 2, and this fx is 0 when x belongs to, so x in the interval of, so when x is minus 1 to 0, in that case fx will be 0, and when x is 0 to 1, in that case fx will be 1. So in that case I need to divide this integration in two parts. So one will be from minus 1 to 0 fx PLX dx plus 0 to 1 fx PLX dx, okay. And in this interval, what's the value of fx? That is 0. And in this interval, the value of fx is 1, right? So then we are left with 12 plus 1 divided by 2, and this term is 0. So we are left with only one term, that is 0 to 1 PLX dx. This CL. This expression of CL is specially for this given function, okay, and this is a general expression. So any function, if you are given any function, then you can generally use this expression, start from this expression and calculate the CLs. Okay, so let me then find out a few CLs. So for example, if L equals to 0, in that case C0 is basically 1 by 2 0 to 1 P0x dx. And what is P0x? That is 1, right? So it is just dx, integration dx, and integration dx is x, and the limit is from 1 to 0, so that means it is only half. If I put L equals to 1, then it is C1 equals to, so if I put L equals to 1, then it is 3 divided by 2 from 0 to 1, it's P1x dx, right? And what is P1x? P1x is x, right? So it is x dx. And what is x dx? So 3 by 2 x square divided by 2. And what is the limit from 0 to 1? And if I put the limit, it will be 3 by 4, okay. For L equals to 2, C2 will be, so 2 times 2, right? 2L plus 1, that is 2 times 2, that is 4, plus 1, 5. So it is 5 by 2, 5 by 2, 0 to 1, 0 to 1, PLX dx. And what is PLX? PL, for here it will be P3x dx. And what is P3x? P3x is half 3x square minus 1, okay. And if you do the integration, you will get 0, okay. And for the next term, L equals to 3, C3 equals to, so if I put L equals to 3, then it is 3 times 2, that is 6 plus 1, 7 by 2, 7 by 2, and then 0 to 1 P3x dx. And what is P3x? P3x is basically 1 by 2, 1 by 2, 5x cube minus 3x dx, okay. And if you do the integration, then the value you will get is basically minus 7 by 16, okay. So then I can write the given fx is sum over CL PLX, L equals to 0 to infinity, and the first few terms will be, it is basically C0 P0x plus C1 P1x plus C2 P2x plus C3 P3x plus dot 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 higher for our terms. Okay, so the C0 I already know, C0 is half. Okay, so it is basically then half P0x plus C1 is 3 by 4, 3 by 4 P1x plus C2 is 0, right? So I will not write this term, and minus C3 is minus 7 by 16, so it is minus 7 by 16 P3x plus dot dot dot. Okay, so this is the function fx. So fx is written, so fx is given function, given fx is written in Legendre series. It's Legendre series. Okay, this is the Legendre series. So what we have learned is basically these Legendre polynomials. These are acting like orthogonal basis vectors. Okay, and any function, any well-behaved function between -1 to 1 can be written as a linear combination of these Legendre functions. So that these kind of ideas, analogies, those are coming from vectors, directional vectors, but there is no directionality here. Okay, so let me give you some homeworks. So homework. First homework is homework 1, which is, so the overall problem is basically you are asked to find out, find the first few terms, maybe 3 to 4 terms of the Legendre series expansion, Legendre series expansion of the given functions. On -1 to 1. Okay, because Legendre polynomials are defined in that range. So homework 1 is fx equals to -1 when -1 less than x less than 0, and when it is 1 when 0 less than equals to x less than 1. Okay, number 2, fx equals to 0 when -1 less than x less than 0, and x when 0 less than equals to x less than 1. Number 3, when fx is p3 dash x. Okay, and number 4 is when fx looks like this. It's -1 to 1, this is the x-axis. And this is 1. Okay, so as a hint for this, I will write the function. Function is basically x function is basically x plus 1. Okay, x plus 1 when -1 less than x less than 0, Okay, and it is 1 minus x when 0 less than equals to x less than 1. Okay. This is how the function is defined. So you can check for yourself, like when these are linear functions, right? So it will be linear in x and it should have a slope of 1. Okay. Because of this length is 1, so this length is 1, this length is 1. That means this angle is 45 degree and tan 45 will be 1. So the slope will be 1 or minus 1. Okay, and it will be linear in x because these are straight lines. And when x is minus 1, then fx should be 0. So if I put x equals to minus 1 here, fx should be 0, and at x equals to 0, fx should be 1, and that's what it is happening. And at x equals to 1, fx will be again 0. So you can see that. So the function will be looking like this expression, and what you need to do is basically, so you need to find out that, okay, fx as CL PLX, sum over CL PLX, L equals to 0 to infinity. Okay, and you need to find out the CLs. And what is CL? CL is basically 2L divided by 2 from minus 1 to 1 fx PLX dx. Okay, so that's what we proved here. So you need to find CLX and then you need to put it back in the series and write a few terms of this series. That's your job. Okay, so that's all for today. So we basically talked about the orthonormality properties of Legendre polynomials, and then we described how we can create a Legendre series if you are given a function. Okay, how we can write it in terms of a Legendre series. So in the next class, I will talk about associate Legendre functions, and that will be the whatever, I mean, that will be the end of this Legendre series or this Legendre polynomials. And after that, I will start Bessel functions. So that's all for today. Bye.